So today I'm going to talk about scientific machine learning. How can we use that for enhance forecasting in subsurface systems? So in the movie here, you're looking at a lab scale CO2 injection experiments. In the left, and in the middle you see a super expensive partial differential equation based simulation which is calibrated with the experiment, and it's a very expensive process to do the calibration. And in the right, you see a machine learning prediction for the same scenario, which is pretty fast. You see that they are synchronized very well. So today I would like to talk about how we can use scientific machine learning to enhance the forecast in applications like this. I am mostly interested in subsurface energy storage. We had a long history of studying subsurface flows, mostly before for oil and gas production, because like even today we are still heavily rely on fossil fuel energy. But nowadays, with a variety of energy resources, it is also very important to have a steady, sustainable energy system. We need renewable energy to be combined with energy storage. So the subsurface is serving as one of the resources naturally that we can use as a system to store the energy and power our energy system. So this is a Nature Review article summarize the challenges to be addressed for large energy storage of different purposes. The subsurface operation is always related to some environmental safety problems because injection will increase pore pressure and many brings geomechanical changes in critical zones and trigger seismicity. So subsurface is a very complex system. We all know about that. Let's take CO2 storage for an example. Even without active chemical reactions, the process has multi-physics phenomena with multiple phases of oil, gas, CO2, and water. So, and in the critical zone, we need to consider multi-phase flow coupled with geomechanics to assess the risk of induced seismicity. And with different geological formations, there will be structural trapping and gravity-related trapping. Here we see different driven forces near the wells. It will be injection-driven flow, and in a much smaller scale, there might be buoyancy-driven flow or viscosity-driven flow. And here it also shows the very different scales in the system. The CO2 plume is in a local scale, and the pressure changes in a much larger scale, and the geomechanical changes even in a far beyond the pressure change area. Also, with the heterogeneity of subsurface, the complexity of the process can be summarized into multi-physics, multi-scale, and full of uncertainties. So we do have physics knowledge about the system over many years, from conservation of mass and momentum. We basically have the multi-phase flow equations here. Now I'm only considering two-phase here, not coupling geomechanics, just for simplicity. So two equations here, one for saturation, one for pressure, and the coupling is through this flux velocity, which is a function of pressure. So this capillary pressure, which is a function of saturation, and you can directly see that the pressure equation is parabolic. So it changes in a larger scale, and the saturation equation is hyperbolic, so it propagates in a smaller scale. Good thing about these equations are they are reliable in providing future predictions with their explanatory power and quantitative error estimates. but it's still very challenging today to simulate physics-based modeling because of the expensive computational cost. For example, here, this simulation based on the simulation of these equations for CO2 sequestration can take many hours, even days, to finish with this resolution. And as you can observe here, this small scale, these beautiful dissolution fingers require to be solved at very fine resolution. So the simulation is expensive for one run, and because of all the uncertainties such as material properties of the porosity, permeability, location of the fault, initial boundary conditions, and also the constitutive laws, which actually is hiding behind the parameters of the mobility lambda here. So it's contribute to a large set of uncertain parameters. So if you represent all of the parameters in P, then it is indeed a parametric system, and the parameter can be of very high dimension. So to assess these different scenarios or design an optimization operation, we will need to run this expensive simulation many times at different parameter samples, and this becomes computationally impossible. So more recently, with the rise of data science, we have data-driven modeling as a tool of many application fields. Pure data-driven modeling, or we say it classical machine learning, it arises from computer science in applications, for example, image classification, where large amounts of data are available, but no physics or equations there. The concept of prediction and error is more qualitative than quantitative. And the same with our daily friend, the popular large language models like ChatGPT. So if we blindly throw a data-driven modeling as a black box for a physical problem, it may fit the data very well in the training, but it may fail immediately at predictions. So this is an example in my previous paper. These solid lines are reference solutions, and the dashed lines are from a pure data-driven model, which has very poor performance in prediction. So it will be dangerous to make big decisions based on these models for our environment, for our future planet, where some small errors can bring catastrophic consequences. So many attributes and challenges in this interdisciplinary area of using machine learning in complex physical systems. Part of my research is about how to use our domain knowledge to embed physics, to respect physical constraints in the machine learning process and improve the machine learning model, the predictive capabilities of the machine learning model, so that at the same time we can take advantage of its computational benefits. So this part is a general methodology development of physics-aware data-driven modeling. And the second part is about how to learn physical quantities of interest from sparse and indirect data. It is true that today we have more data than ever, but when it comes to many complex engineering problems, geoscience problems, we know the data are often sparse, both in time and space. They can be noisy, they can be indirect. So also despite the cost of sensors and the technology around it, we also don't want to live in a world where our Earth is literally littered with sensors. So the data are always gonna be sparse. I will go back to the specific application of the CO2 sequestration there and show you how we embrace this challenge in particularly two projects. And one is how to learn from spatially sparse quantities of interest directly when the mathematical models often do not exist. And the second is how to integrate with experimental data where measurement is often indirect and noisy. So I'm gonna go very quickly in the first thrust and go to more details of the second one. So basically, the first part is more around the methodology development. Mostly, I was doing this during my PhD. Basically, we are studying a pure data-driven modeling tool called dynamic mode decomposition, DMD in short. We find standard DMD fits the training data very well, as I was showing in the previous video, but it fails at learning the true dynamics for the physical systems. Like the movie I showed earlier, we can see it fits the data very well, but in prediction, it's just totally off. And we developed a variety of methods to blend this data-driven modeling tool, DMD, with physics-aware ingredients to enable the predictive capabilities at low computational cost. So we had some results for extrapolation error bound, had some treatments for advection-dominated systems, shock propagations, and so on. So I'm happy to talk offline if you find any of these topics are of your particular interest. But today, I would like to focus more on the second part. And let's see the first challenge of integrating sparse and indirect data. So back to the CO2 sequestration example, besides pressure buildup and plume migration, another critical issue is the environmental safety. Because of the rock mass movement, there are faults in the complex deep sedimentary formation. And with pressure building up during the CO2 injection, volumetric expansions bring geomechanical changes that may induce seismicity in critical zones. And these geomechanical changes reflect in changes of shear stress and normal stress in fault zones. When normal stress is very large and the shear stress is small, you can try to push your hands more in the normal direction and less in the shear direction. Slip will not happen. But when normal stress is small and the shear stress is large, slip will happen and that brings earthquake. So it is really this ratio of shear stress and normal stress we call slip tendency that serves as an indicator of fault instability. So when the slip tendency goes beyond a threshold, seismicity will be induced. If we want to estimate this slip tendency, this risk indicator, we start with relevant fault property and let's say fault permeability. Conventionally, it is measured from a wide range of host rocks and then estimated by a deterministic, isotropic, homogeneous value from empirical models. Then, with this one value representing the fault property as the input, expensive numerical simulation is running for physics-based models. And in this case, it is a multi-phase flow coupled with geomechanics derived from conservation of mass and balance of linear momentum. Here, I'm showing an example of a reservoir model with faults. The storage aquifer is confined by two layers of low permeability cap rock. And this multi-layer system is intersected by a pre-existing normal fault. And the CO2 is injection happening here. And after post-processing, one will get this quantity of interest, as we mentioned before, the sleep tendency, the risk indicator. Here, this video is showing a dynamic evolution of this sleep tendency. And this vertical red line here indicates the threshold. And we can see the sleep may happen at later time at the intersection of the storage aquifer and the lower cap rock. So with everything deterministic, this conventional procedure gives us one fixed estimate of the sleep tendency. However, in reality, we know it is very inaccurate to estimate this fault probability, this fault probability by one value. As we see from this video, the formation of the fault shows that the probability of the fault could be and should be very heterogeneous and with a lot of uncertainties. So this is from previous work in my postdoc group with Ruben Juanes and Luis Salo. We replaced this previous one value rough estimate with a heterogeneous, anisotropic, and a stochastic model for the fault probability. And we have Luis developed this very handy computational tool called predict. And to do the sampling for the fault probabilities. We can also take other sources of uncertainties from the reservoir to mimic the reality as well. So with the samples from the uncertain inputs, one has to do a large number of Monte Carlo runs, and each run will give us different estimate of the sleep tendency, the quantity of interest. With a large number, we can calculate some quantiles of this quantity of interest and evaluate the risk statistically. However, the computational challenge is these expensive simulations needs to be run repeatedly in Monte Carlo. So to tackle this challenge, the thing we want to do is replace this expensive simulation and post-processing process with efficient machine learning model. So we built a direct machine learning model from the input uncertainties to the output quantities of interest. And once built, the model can predict in no time from the input to the output. And this becomes a critical enabler for uncertainty quantification in Monte Carlo for loops. So let's dig a little bit more of this direct machine learning model for the interest of our problem and many, many more. We are not interested in or having access to the data of the quantity of interest over the whole domain. And in our case, we only care about what will happen along the fault, which is this green area. So we want to build a model directly and only for the quantity of interest, the sleep tendency along the fault. And in fact, a large part of the domain provide very little information as we observe. So the goal is, again, to construct a model from the sparse data of the sleep tendency only in this particular region. The challenge is, although we have the mathematical model, which is the multi-phase flow coupled geomechanics PDE, for the full field solutions of saturation, pressure, and stress, mathematical models for this quantity of interest, the sleep tendency itself, in this particular region of the fault, it often does not exist. You cannot write it down explicitly. And we want to learn this direct model. So motivated by the so-called Morris-Zwanzig formula, I'm not going to the mathematical details of it. So you can refer to this mathematical papers here, they designed a neural network structure that incorporate some past history of the quantity of interest so that for the future trajectory, it can be learned from the sparse data, but with history. And we can add the parameters values also here, and then we train the neural network from the trajectory of different parameter samples. And then after training, predictions for another parameter input, which is not in the training, can be conducted recursively. So here I'm showing the comparison of the probability distribution obtained from the reference solutions using large number of expensive simulations in Monte Carlo. So showing here in blue and red, the blue is the reference solution using very expensive simulations, and the red is the prediction using the direct machine learning model. So as we can see here, although the distributions of the sleep tendency change significantly over time, and the machine learning model is able to capture the overall shape of the distribution. The differences of these two distributions increase over time as errors accumulate over iterations. Here, we plot the 10th percentile of the quantity of interest, the small number of training data set showing here in blue dot curves. It provides a very poor approximation to the statistics of the reference, which showing here in the black solid curve. And again, the reference is large number of Monte Carlo runs with simulations. However, using the same small data set combined with our direct machine learning model, which can reproduce a large number of accurate ensembles, and we can use that to approximate the statistics with much higher accuracy. So showing here in red, as you can see, it provides much, much better approximation to the solid reference curve. And the same for the 50s, the 90s percentile. And the training of the neural network is a negligible fraction of generating the data because the quantity of interest is of small dimension. The neural network doesn't have to be big. Basically, the speed up for this UQ task is significant. And using about the same computational budget to generate a small set of training data with a little bit extra effort in training neural network, we can get a much higher accuracy in this quantiles estimation. So with the two novelties in this total framework, we bring in realistic uncertainties to the system. And we use the machine learning model, the direct machine learning model, to enable accurate uncertainty quantification. And we can make real-time assessment of the induced seismicity risks, as well as, for policy making and remediation plans for CO2 sequestration. The same framework can be extended with adding some physics-informed observations to provide more information for the learning process and improve the learning performance. This can be obtained from our existing physical knowledge about the system, as well as measurements from sensors in reality. For example, displacement on the surface of the domain, or the pressure measured from monitoring wells. These are all typical settings in a CCS project. And also some control parameters from the input can be added there. And one can also add other quantities of interest in the output. You can see in our paper, we also considered pressure buildup and CO2 leakage. The workflow is the same. And we can also use that for sensitivity analysis of the output respect to the input parameters. We have some results in the WR paper last year. Okay. So a little bit more towards what I'm doing nowadays. This is the previous work I'm showing. Another example here is the classical quarter-5 SWOT example. We have a random permeability field, one injection well, one production well, and traditional way would need full field simulation of the pressure field. Although the quantity of interest could just be the production rate in this northeastern corner, and of course we can use the same framework as before I described to replace the full field pressure simulation by partial history of the quantity of interest with a parameter. But a more recent methodology work, we can actually learn the quantity of interest in next time step from just the past few steps of trajectories only without having the input of the parameters. So this can be better deal with the practical setting that the parameters are indeed the uncertainties, and the uncertainties here are our permeability fields. All we need in the training is to collect chunks of the input and output pairs of the data from the trajectory of production rate as a training data. And we need no knowledge about the underlying uncertain permeability. Then in the testing phase, we only need a small time interval to start because we need the history, so we need a small interval to start. And then the model can do pretty good prediction afterwards, again, without the input of the uncertain permeability fields. So this is a quite boring example. We only see this decaying there. But this is our ongoing work, still very early, and we tested 100 cases. We got promising results and good accuracy, and we want to try this framework to more complicated systems and see how well it goes to push the boundary of this. All right, so I want to move to the next part about the how to integrate with experimental data, which is my first slides video there. Maybe many of you know about these fluid flower experiments. It's fantastic experiments to help us bridge the gap in the case that we have these not available data to validate all our existing models against the measurement data because of the long time scale of the real CO2 sequestration. So this experiment is happening at the University of Bergen. It's called fluid flower. So they have these meter scale quasi-2D tanks with transparent glasses panels, and different geological settings are constructed by pouring different kinds of sands to mimic layers of the reservoir, the seals and the faults. And CO2 is injected at designed locations, and the plume migration is visible to track in this days-long experiment. And it also adds some sensors in the back of the tank to collect pressure data. And they have a series of experiments with different size, geometry, injection designs of the tank. And they are continuing these experiments in museums and in classrooms, very cool, to educate the public about CO2 sequestration. So this experiment is also used as a basis for a benchmark study participated by 9 groups around the world. Basically, the best simulators around the world. So around the world. So they want to see if our best simulators can validate a real CO2 sequestration scenario, even just in a lab scale experiment. So the experimental data is not given to the simulation teams before they do the simulation. So the only base accessible to every participating team is the initial geological and the petrophysical characterization and the size and stratigraphy of the tank, the room temperature, pressure, and so on. And it's a double-blind study. No interaction between the experimental team, simulation team, and no communications among the participating teams. So the simulation teams are starting with about the same equation, the multi-phase flow we're talking about. But there are many uncertain parameters in this system. It has to be estimated by the simulation teams independently, especially the constitutive laws here for the relative permeability. Most of the teams are using the quarry type model, which has these uncertain parameters in the exponent. And you can imagine how sensitive it will be to the system with a crazy exponent here. And for different simulation teams, they have also different numerical choices, such as the mesh size, the convergence threshold, these kind of things. And here's the fun part. The results of this double-blind study, they compare the simulation predictions with the ground truth experiment. This is for 24 hours. The yellow contours are resolved CO2, and the blue contours are gas CO2 from experiments. And the green shades are simulated dissolved CO2, and the red shades are simulated gas CO2. So ideally, the green will match the yellow contours, and the red should match with the blue contours. But you can obviously see the big gap between the ground truth experiments with our best simulators in the world. And especially for several teams, we can see that this vertical plume is very challenging, and that's because of the existing faults there. There will be a plume escape from the faults over there, and several teams cannot capture that. And for longer time, this is 120 hours, it's getting worse. Again, one of the reasons of this big gap is that the experimental data is not given to the participating teams as a prior, and the many parameters, especially the constitutive laws in the system, are chosen by the team members. So without history matching, we will have this big mismatch as expected. And things can be improved immediately after model calibration history matching. This is a simulation results from an earlier work of Rubin and Lewis. So after this manual calibration, after history matching with experimental data, you can see the simulation model provides a good representation of the experiments. But if you ask Lewis, who went to Bergen and stayed there for some time, he manually did the history matching. He will tell you how painful that history matching process is. There are so many parameters to be fine-tuned in the system. Some selections can be made with his geophysical intuitions, but in general, we don't know how sensitive the system responds to each parameter changes. And the simulations are very expensive, as we mentioned before. And we need, very fine resolution to resolve these beautiful small-scale dissolution fingers. So to lift the pen in this manual history matching, I was working with Ruben and Lewis, and we want to use machine learning in model calibration history matching. This is still ongoing work, but we already have some results for surrogate modeling continued with the history matching. We learn a machine learning model is an evolution model from the input parameter samples in parameter space to different output CO2 migration plume. And what we want to do next is use this learned machine learning surrogate to do quantitative sensitivity analysis and do the history matching with the experimental data. And the final product we had in mind could be a digital twin for the fluid flower experiments. And the calibrated model should allow us to do things like transfer learning to different scenarios of geological formation and injection plans. So I am super excited about the project as, a first step to enhance our confidence in a trustworthy prediction and a real-time assessment for CO2 sequestration, even we're just in a lab scale. So as an input, we have three material regions: the storage aquifer, the seal, and the fault. And we have different properties: the permeability, the capillary entrance pressure, concatenated water saturation, and water relative permeability exponent, the gas relative exponent we used in the Corey constitutive laws, and relative permeabilities. So 3 times 5, we have 15 input parameters. But what is important here, we borrow the spatial structure, the stratigraphy of the fluid flower tank. So we actually, instead of using the 15 input parameters, we actually using these 5 images and given the resolution of our choice to represent all the parameters. There are some challenges that we have to face. One is, of course, the 15-dimensional parameter space. It doesn't sound like much, but it cannot be sampled densely. If you want to have 5 parameter values in each dimension, it goes to billions of combinations. That's a curse of dimensionality. And that's one challenge. The sampling is going to be sparse. The other challenge is this experiment is conducted in ambient pressure condition, and the buoyancy of CO2 at this condition makes it very challenging for simulations to converge. And this is a plot of the combination of the 15 parameters that leads to simulations to complete and not complete. Here, the simulation tool we use is the MATLAB toolbox for reservoir simulation, MRST. We see the overlap with each other of all the cases, and they're all over the space. So we cannot really determine which region in this 15-dimensional space will lead to failure simulations. So we just need to embrace this challenge. It also reflects the fact that the data is always going to be sparser and more limited than we wish. So that makes to the input and the outputs we decided to use the full field maps as our quantities of interest. We also have the time as the 6th channel as the input to the output, resolve the CO2 map. And here we use UNet, a very popular convolutional neural network architecture that is tailored to image regression to do this learning task. And we have the training set that are very limited, about 80 simulation of the parameter combinations, but we have 466 time steps, so that's 80 times 466. Then here we have the test results of a new combination of the parameter that is not seen in the training. So showing here, the columns are representative different time snapshots. And the first row is reference truths from simulation. And the middle row is a machine learning predictions. And the last row is point-wise error map. So I want to point out that this is a very challenging task because a big part of the error actually attributes to the pointwise the distribution fingers from hydrodynamic instability. So it's a very challenging task. But overall, the plumes has been matched pretty good. And just to quickly show you another test results where we have similar good match, but very different plume features, as you can see here. And now we have the histogram of the Wasserstein distance between the test case of all the simulations and the entire training data set of the simulation at four different representative times, showing here in the blue bars. So essentially, it shows the diversity of the data set and the complexity of the distribution, especially we can see that bimode's behavior in longer time. And this evolution of a similarity measure basically reflects that our test case is not a trivial interpolation from the training data because it's different from the training data set. The red vertical line is the Wasserstein distance between the test case simulation and the test case machine learning results. We see it a better measure of accuracy because the previous pointwise error mostly comes from the distribution fingers, and Wasserstein distance is a better measure for the plume migration. So we see that the machine learning prediction accuracy remain like less than 10 to -3, even when the diversity of the training data set spreads out over later time. So we can imagine that if we use trivial interpolations like Kriging's or other tools, it might do well at the beginning when the data patterns are quite similar to each other, but will definitely do worse at later time when diverse patterns appears. But in contrast, our machine learning model is able to maintain the accuracy because of effective learning. And we are basically summing up the blue bars in the previous slides at the bottom, and the relative accuracy is defined by this. And since the top remains the same order of accuracy over time, basically showing in the red vertical lines in the previous slides, and the bottom diversity is increased over time, so this relative error is decreasing over time. And this reflects the relative accuracy of our machine learning is enhancing over time. So it makes sense, as we know, machine learning is a data-driven method. It will learn better from a more diverse data set when more information from the data comes. It shows the fundamental difference between machine learning and conventional interpolation method. So a little bit preliminary results from the model calibration part. Now we use this developed convolutional neural network-based surrogate model to compute the posterior distribution using MCMC, shown here in the gray histogram. And we use the manual history matched parameter values from Lewis as a reference here, showing here in red. So I call it human learned, and the gray one machine learned. So we see that here are three of the parameters. For some of the parameters, for example, this SWC in the region E, the posterior is well constrained around the true value, indicating a strong identifiability. But for other cases, the posterior for some other parameters, showing a strong update from the posterior. The true value here is closer to the lower tail of the posterior, suggesting a partial identifiability. And the value here is towards the left tail and indicating some bias and challenges in the inference. We all know that this ill-posed nature of history matching and multiple parameter combinations may match the observation data as good as or even better than our reference solution identified manually. So we need a robust surrogate model to fully explore the space of all plausible solutions. We also need to revise the prior and assess inferred parameter combinations using domain knowledge. For example, this strong skewness observed in here may suggesting that we need refined prior towards higher values, and some inferred combinations may also be physically implausible. So that shows we need some further validations through maybe high fidelity simulations and experimental data and to guide and constrain the parameter identification process. Anyway, the current surrogate model was trained with a limited data set. So we are also switching to commercial simulators to get more data and train a more robust surrogate model. And we are also thinking about more advanced surrogate models, like, for example, graph neural network, which can serve as a better candidate when we have these irregular meshes, especially very fine meshes around the faults and things. So I'm gonna go quickly here. Some ongoing collaborations with people doing graph neural network. And from some preliminary studies we have there, we do see that graph neural network can do a better job, especially at the boundary adjacent meshes and adaptive mesh refinement and some more complicated geological features. So we see some promising results from there. Just some wrap up from this takeaway and for some ongoing work, we see that the machine learning model is able to learn from a very limited data set effectively, and the speed up is significant. It's still some early stage work, and we have a lot of ideas to improve the accuracy and the robustness of the machine learning model, including the graph neural network. And hopefully the accurate machine learning surrogate will ultimately allow us to do sensitivity analysis and better model calibration, history matching with experimental data, and which will not be impossible without machine learning surrogates. So in the end, I think it's towards the development of digital twins we had in mind how to make all of this in real time, how to generalize this to different geological formations and tank sizes to different scenarios, and how to also enable some objective-oriented tasks, for example, optimization or real-time controls of the injection and risk controls. And of course, more challenging questions would be how to extend the current framework where we have the luxury of full field data in the experiments, how to extend this to reservoir and basin scales in our real life, where we don't have the luxury of full field data. We only have indirect data, sparse data. There will be more challenging questions to address in this framework. And hopefully machine learning can help us with some aspect of it. All right, I think it's exactly like 15 minutes. I'm happy to end here and take any questions you have.
All right, Hannah, thanks so much for a great talk. We have a few questions here. Let's see. This is from Wen Chao. Why do you think it is valid to compare simulators with different numerical methods?
Sorry, I'm trying to see the chat. Is it in the chat? No.
It's in
No,
the
it'll be in the Q&A.
Okay, I see that. Why do you think it's valid to compare simulations with different numerical to compare simulators with different numerical methods? Did you mean that, like, for example, for the fluid flow benchmark study, we have different participating teams that choose different simulators with different, for example, mesh sizes and convergence simulators? Yeah, I think it's about a more we have the PDEs, most of the teams using the same multi-phase flow equations, but depending on how you numerically solve the equations, um, because we need the visualization, we need to numerically solve the solutions, and we want it to be reliable in terms of using it for predictions for other practical uses. So I think it's very valuable that different participating teams are using different numerical methods, and we can explore what will be the most efficient, the most reliable, the most stable algorithm to simulate all of these scenarios. Yeah, I think there's still a lot of challenges in terms of convergence, which I ran into this a lot for different parameters. Uh, some of the simulations can converge in 2 hours. Some of other parameter combinations, it never converge. And one of the reasons we switched to commercial simulators, they probably have some secret source in terms of preconditioning and things there. It makes a much higher convergence rate. Yeah, it's all very, very interesting and challenging numerical questions. Sorry, next one. I can read it if
Okay, great.
okay. How might you incorporate the tanned plume migration along artificial features such as a injection-induced simulation fractures or B, the drilled whale bones? Yeah, that's a very good question. So I would say that because the machine learning model we get from here is trained from the simulation data, and the simulation is run by the multi-phase flow equation, which I don't think it includes the physics of, injection-induced fractures. If the simulation data itself does not include all of the scenarios, the features you mentioned here, we of course wouldn't expect the machine learning model will learn these features in the model. But one thing I think is promising, which is the transfer learning part I'm excited about. Hopefully the machine learning model already learned the multi-phase part of the physics there. And when we run some efficient data, a small amount of data, which incorporate these additional features, and we can use transfer learning with a small data set, and based on a small effort of retraining a few layers of the neural network, we can use transfer learning to include all of these additional features. That will be an efficient way to incorporate these things. Hope it answers the question.
You have another question. You said thank you, so you did.
Okay, good. I didn't really catch on where you embed the physics in the deep learning methods that you used here in your work. Did you use some PD residue like in pins, or is there any other treatment to make the DL-based surrogate to be more physics aware? Yeah, so here I would say that the physics part is we are not only using it for the surrogate modeling of prediction, we're also using that to identify the physical parameters back to the PDE system. And you can regard it as long as we identify the combinations of the physics, we can also represent it in the simulation. It's just if the machine learning model is accurate enough for this combination, we also trust it to represent the simulation as well. And indeed, we are also considering some incorporations with this pins idea because the current setting, we have very limited data set. And one idea we had in mind to compensate for the limited data set is using some PDE residuals so that hopefully can allow us to use less data with using the PDE residue in the loss function. that is also something we had in mind. What do you think about the cause of seeing larger discrepancies between the simulations results and fluid flow observation at later times? Yeah, I think every simulation, because all of the simulations are more evolution over time, um, all of the numerical errors of any particular scheme, we learn from the stability analysis that the error is always accumulating over each time steps. So I think we all start from an initial condition which has less uncertainty, and we start from there match very well with experiment. But then after each time step, the small accumulation of the error happens and it accumulates over time. So I think we expect that later time, we definitely have the error accumulated over many, many time steps.
All right. It looks like we took care of all the questions.
All
I want
right,
to thank
great.
Dr. Liu again for a wonderful seminar. Please stay tuned. We will be having another series of webinars of SciM Geoscience webinars this spring. Make sure that you're subscribed to the SciM Geosciences community pages, and don't forget to renew your SciM membership. Thanks everyone again for joining us today.
Thank you, everyone.
Thanks, Hannah.